High-power systems operating on 800-volt bus architectures, like solid-state transformers, photovoltaic inverters, and EV motor drives, require extreme power density. Upgrading a system's efficiency from 98.8% to 99.38% might sound like a negligible 0.6% gain. But mathematically, that exact fraction dictates the physical limits of the hardware. In a 378 kilowatt output system, this 0.6% delta translates to cutting the total thermal waste heat exactly in half. To achieve this drastic reduction in heat, the industry is aggressively replacing legacy silicon insulated gate bipolar transistors, or IGBTs, with silicon carbide MOSFET architectures. We are going to analyze exactly how this is done using the basic semiconductor ED3 silicon carbide MOSFET half-bridge module. This schematic shows the internal circuit of the ED3 module. It features a 1200-volt rating, a 540-amp nominal current, and a highly optimized half-bridge topology configured across pins 4, 10, 11, and 3. Achieving a 50% heat reduction requires an integrated design approach, starting from the base substrate mechanics and extending all the way up to nanosecond switching dynamics. Let's start with the foundational layer. In high-density modules, the ceramic substrate is critical because thermomechanical stress is the primary cause of hardware failure. This diagram compares the available materials. Historically, designers faced a strict trade-off. Alumina is cost-effective, but thermally insulative. Aluminum nitride offers excellent thermal conductivity, but is highly brittle. In high-temperature silicon carbide applications, the low fracture toughness of aluminum nitride causes it to crack and delaminate after 1,000 thermal shock cycles. The ED3 module solves this by utilizing a silicon nitride active metal brazing, or AMB, substrate. AMB is a joining process that chemically bonds the metal and ceramic layers together to withstand extreme stress. Silicon nitride has a lower raw thermal conductivity of 90 watts per meter Kelvin than aluminum nitride. However, its massive bending strength of 700 newtons per square millimeter allows engineers to manufacture much thinner substrates, down to 360 micrometers. Because it is so thin, the silicon nitride substrate matches the overall thermal resistance of thicker aluminum nitride options while providing vastly superior mechanical durability. Empirical testing shows that these silicon nitride substrates survive well past 1,000 extreme temperature shock cycles with zero copper delamination. This structural integrity ensures that designers can push the silicon carbide module to its absolute power density limits without risking packaging failure. With the mechanical foundation secure, we move to electrical validation. We characterize the switching efficiency using an industry-standard double-pulse test. Here is the physical test bench setup. The module under test is wired directly to a high-speed oscilloscope to capture precise voltage and current transients. For this characterization, the 1200-volt module is tested with a 600-volt drain source voltage, pushing currents up to 540 amps across temperatures ranging from 25 to 175 degrees Celsius. Looking at the test circuit schematic, the half-bridge is connected to an inductive load. A pulsed gate signal is applied to isolate distinct switching events for measurement. This chart shows how we define the specific energy loss parameters. Turn-on and turn-off losses, known as E-on and E-off, are calculated as the mathematical integral of the drain current and drain source voltage crossover over time. Accurately capturing these nanosecond transients is necessary to validate the theoretical efficiency advantages of silicon carbide over legacy silicon. This chart displays the turn-off transient at 270 amps. Notice the exact intersection of the falling drain current in blue and rising drain source voltage in orange. With voltage slopes exceeding 20 kilovolts per microsecond, the calculated E-off energy is extremely low, measuring just 2.4 millijoules. This next chart shows the corresponding turn-on transient at the 270 amp load. The timing markers isolate the current rise time, revealing an incredibly steep slope yielding an E-on of just 11.61 millijoules. Even scaled to 540 amps, total switching losses remain tightly controlled. Furthermore, the intrinsic body diode exhibits a minimal reverse recovery charge, known as QRR. This lack of recovery current prevents additional switching-related heat from accumulating during operation. The combination of nanosecond scale transients and low reverse recovery charge yields a switching loss profile that legacy IGBTs simply cannot match. We can now map this bench data onto a real-world simulation, a three-phase inverter operating on an 800-volt DC bus, drawing 400 amps per phase at an 8 kHz switching frequency. This bar chart compares the single-switch total loss in watts between the basic silicon carbide module and competitor IGBTs from Fuji and Infineon, all under identical 378 kilowatt output conditions. The final simulation data shows legacy IGBTs peaking at roughly 98.8% efficiency, while the ED3 module hits 99.38%. As stated earlier, this 0.62% difference has massive physical implications. It means the legacy IGBTs generate double the internal thermal wattage compared to the silicon carbide MOSFETs. Moving to silicon carbide physically changes the thermal topology of the entire system. It allows engineers to shrink heat sinks, reduce cooling volume, and lower overall system costs. However, managing voltage slopes are 20 kilovolts per microsecond requires specialized gate drive features like active Miller clamping. We will explore how to safely drive these modules in our next analysis.